So it's my pleasure to introduce Matt White. So Matt has so many titles, I had to take notes on them. So he's an associate professor in the computer science department at Utah. He's also a strategist in the executive office of the president at the White House, which I guess you can tell from that. He's a visiting associate professor at Harvard Medical School, and he also has several other titles, including co-founder of Paranomics and president of the NGLY1 Foundation, which I'll tell you a little bit about during this talk. So his CS research is on static analysis, and that ultimately led him, after some personal things that he'll tell you about, to fighting the war on error. So thanks very much, Matt, for coming here and giving a talk.
Well, thanks, Jeff. It's a pleasure to be here. And actually, it's a pleasure to see so many familiar faces. I think I've seen a number of you out of Utah or Harvard at some point. And I just have one disclaimer at the start. So this is not an officially approved communication. So anytime I give a talk like this, I have to actually put this disclaimer up, which is that this is a personal talk. And it may or may not reflect the views of the president and his administration. However, you never know. It just might. I personally have not had a deep conversation with the president about his policies on halting problem, but but as the ranking field official at the White House, I think I have some license to interpret for him. All right, so let's get started with the war on error. So let's just start off with an observation that error in code is bad. I think we can all agree with that. And there's really two kinds of errors in code out there. There's errors in code for software. I think most of us in this room are very familiar with these kinds of errors. So since we're talking about software, this is the obligatory rocket blowing up. Whenever we talk of this sort, that's the Ariane 5. I think it was like $1 billion software error. And then we have software errors like Heartbleed, which are like $1 billion security vulnerabilities. So yeah, it's clear that error in code for software is bad, but that's not the only kind of code that's out there. People are also made of code. We have DNA, we have genomes, and when you get errors in that code, bad things happen to us. You get rare genetic disorders, you get predispositions for chronic diseases like heart disease, and you get cancer. These are things which I would say are diseases of the genome, and they're bugs in our code. And I think as soon as we think about them that way, it sort of highlights how we want to go about fixing them. And I think the argument I want to make today is that we can fix both kinds of errors. And I'll even do my best to come up with a unifying theme. This is not, I try not to do an A and B talk. So my unifying theme is approximation. That we can use styles of approximation to come up with ways of solving both the halting problem, which leads to ways of fixing errors in software, and approximation to solve problems we want to face that come up when we're trying to fix errors in code for people. So there's really two main ideas, and the first main idea is, I think we can all imagine, and I'll go into some detail on this later, that if you could solve the halting problem, you could do lots of really cool things for reasoning about software. So the halting problem would say, if it existed, if a solution to it existed, it would be some function that maps a program into it halts or it doesn't. Now, obviously we can't do this, but what we could do is approximate the solution to the halting problem. We're going to do this in much more fine-grained detail, and say, well, it'll either halt, not halt, or I don't know what it does. Because you can always say, I don't know. And as soon as you give yourself the license to say, I don't know, you can have the sort of default version of this, which just says, I don't know all the time. And then the game becomes, how little can you say, I don't know? How often can you give a precise answer? And when it comes to people, we want to compute another kind of function. We want to take a function that takes a person, or really their genetic data, that accounts for the individual mutations that make them who they are, and what's driving whatever their disease state is, and map that into the right medication for them, the perfect therapy, the perfect treatment. So we have another function that we're trying to build out over here, and this function is also very difficult to compute, so we're going to approximate it as well. And the approximation here is going to either give you back the right medication, or some approximation of the right medication, or a set of medications which could be right for them, or you get back a set of experiments that you should run that might point you in the direction to go to find out what the right medication is, because you might actually have to make that medication if it doesn't exist yet. So this is the process that I'll sketch out later on. So let's talk about fixing software first. So let's also know that software is terrible. We're living in an era where not only do we have like these mega bugs, mega vulnerabilities, which get their own logos, they actually also have their own product line. So we've sort of reached a pivotal cultural moment in information security. And these things really do cost billions of dollars at this point. It's all generally very distributed in that things, but it's definitely a major drag on our economy. And the kinds of things that you can hack is just sort of exploding. So we don't seem to have a good handle on sort of the scale of the information security crisis quite yet. It's only getting worse. And it seems that the number of places and contexts in which you need information security is growing without bound. And if you're wondering why it is you might need information security in a restroom, all that means is that you clearly haven't been to Japan. Where I'm sure the toilets are already hackable. So why are we in this problem in the first place? Why is everything so insecure almost by default? Well, I think this tweet sums it up quite nicely. Which I think is the prevailing attitude for how we develop a lot of software today. So, I mean, I think this really does get to it. You know, we write a lot of our software in insecure languages like C, and then we write vulnerabilities in them because we're just not very good at using them. And I don't think this is going to change anytime soon. Yeah, I think C is not going anywhere, unfortunately, even though we have much better languages to use. So what are the solutions that are out there? Well, what we really need to do in general is engineer software. So what do I mean by engineering software? Well, what's interesting is that we have a field, we have an academic discipline called software engineering. I'm just going to tell you right now that software engineering is not actually engineering. Because if you're an engineer, a classical engineer, you're going to use things like prediction to be able to reason about the artifacts you're building in advance and sort of get a sense of what it is that they're actually going to do. And if you're, you know, most engineers are going to at some point fall back on something like F equals ma to build their predictive models. So, for example, if you know the force, you know the mass, you can get acceleration. From acceleration, you go to velocity. From velocity, you can go all the way up to distance. And you can predict things very precisely using a formula like that. And so, for example, if you're a military engineer, you want to predict the path of a projectile from one ship to another, you can do that very precisely using ultimately F equals ma. And that's not something you can do necessarily in computer science. But, you know, and to highlight the sort of distinction between how we do things in computer science versus how we do things in other engineering, let's look at bridges. And let's also look at this Calvin and Hobbes cartoon. So, you know, this cartoon, like, it immediately came back to me when I was an undergrad taking software engineering. I thought, oh my God, this cartoon is so applicable because this is exactly how we build software. So you know, Calvin asks his dad, how do they know the load limit on bridges? And his dad says, well, they just drive bigger and bigger trucks or test cases across the bridges until it breaks. And they wait the last truck and rebuild the bridge. And again, that's not how we build bridges. But it's so obviously how we build software that I think this very clearly highlights the distinction between, you know, real engineering and whatever software engineering actually is. Because again, if you want to build a bridge, you have, you know, again, going all the way back to F equals ma, you have statics and dynamics to predict, you know, what the forces on this bridge will be and what the tensile strengths have to be in order to actually have this bridge stand the test of time. So again, you know, real engineers have predictive tools. They can take a formal model and reason about what's going to happen to the artifacts that they're dealing with. So, can you predict the behavior of software? Do we have, you know, a formal model that will allow us to do this in general? No. Mike says no, and Mike is right. Because Alan Turing said we can't do that. So we're just sort of stuck, you know, from the founding of our field with this impossible problem. Yeah, so you know, you just can't in general decide the halting behavior program. And of course, you can take this impossibility and transfer it to lots of other impossibilities, like finding discrete vulnerabilities with, you know, with perfect accuracy and stuff like that. So whereas, you know, in fields like physics, you have you know, event horizons and black holes beyond which you cannot see. In software, we really have the loophole. These are the event horizons beyond which we cannot really reason. So what can we do? If we can't solve the halting problem, but we need to solve the halting problem, you know, in practice, what are we going to do about this? Well, there's several things we could do. So I mentioned that, you know, one reason security is such a problem is that, you know, we're using languages like C and C++ to do stuff that we really should not be using them for anymore. So we could switch to better languages. We could stop using C and C++ to do, you know, pointer bumping driven parsing of network packets. We could switch to, you know, more superior 90s era technology, or we could try, you know, strictly superior technology altogether for constructing our programs. You know, we could actually prove, you know, from the get-go their absolute correctness and security properties. Not that long ago, I was actually in a pretty large DARPA project that was exploring this avenue to information security, where we would build the languages, the platforms, the OSs that would be sort of secure by default and much more secure than we're used to right now, using a clean slate approach. Now, I'm not going to talk about this today, but I want to talk about today's static analysis. But I don't want to pretend like this is the only way we can go about getting security for our software. There are other approaches too. But the reason I like what I call the static analysis game is that this allows us the opportunity to go back to legacy code, because we don't have to rewrite everything. If we're going to analyze old code and look for the possibility of errors and vulnerabilities. So the way that the static analysis game works is you can imagine that your program is, the execution of your program is a trajectory through some state space over time. This is what you sort of start here, sort of your model for what your program is doing, and then you want to come up with some upper and lower bound on the trajectory of this program. So that would be a static analysis. You can't know the path exactly, but maybe you bound it in some way. So you say, it doesn't go into this region, it doesn't go into this region. And then what you do is you check to see, does this region that you predicted will go through intersect with regions where it looks like there are security vulnerabilities? And in this case, the program doesn't necessarily have a buffer overflow, but because the analysis wasn't quite precise enough, it thinks that it may have a buffer overflow. And at this point, you want to come up with a more precise static analysis that still doesn't touch the line, obviously, but gets closer to it. And then this can actually rule out the presence of that buffer overflow. So I think this, in a nutshell, is what we're doing in the static analysis game. We're trying to build ever tighter approximations of the trajectory of this program without actually touching that line, because that would mean solving the halting problem. So how do you play this game? Well, you're lucky here at Maryland because you could just ask David. David's been a co-conspirator of mine for a number of years, so I'm going to talk about some of the work that we've actually done together, because it sort of forms the foundation of an entire research program and how we think about solving, or really approximating solutions to the whole problem, and doing program reasoning. And that framework is abstracting abstract machines. And this work is actually quite remarkable in how it sort of just took off. It appeared in ICAP 2010, and then immediately got picked up as a research highlight in CACM. And then from there, it got invited as a best paper by ICAP into JFP. And it seems to be very, very quickly being adopted by other researchers as a platform for building a baseline system for reasoning about a program and what it's going to do. And what's nice about it is it's very pluggable. You can start adding lots of stuff into it and tweaking the framework in interesting ways once you've got this sort of baseline analyzer for your language. And the key idea here is that we're going to take effectively an interpreter, or really an interpreter without side effects, which means it's semantics, and turn it into an approximator. So that when programs go in, instead of interpreting their meaning, it will approximate their behavior. And there's really sort of two key ingredients you have to have in place in order to use this abstracting abstract machines methodology. You need a way of taking a program and injecting it into a machine state, and then you need a way of taking one machine state and going to the next. So if you've got this, chances are pretty good you can apply abstracting abstract machines to get yourself one of these approximators. So what this looks like at a very high level in practice is you would take a semantics like this, and you could actually push it through and get an evaluator like this. So you take a program and you inject it into an initial machine state, and then you apply step. Go step, 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 step. And right away we think of one way of looking for vulnerabilities this way, which is, okay, take your program, inject it into a state, and just keep stepping it until it stops. And then just look at every single state you visited and check to see if there was a vulnerability. But this obviously doesn't work in practice because programs don't always terminate. The program could go up without bound. And because of that, we need to come up with some way of approximating the set of states that might be visited. And that's ultimately what abstracting abstract machines is going to do for you. So, but we're going to apply the same idea there. Come up with some approximation. Yeah.
Actually, I was going to say, I'm going to help you. So the waiting until you find the vulnerability might also be too late, right? Because in the Arion 5 case, if it discovered when it was right about to blow up that it's about to blow up,
Well, yeah. Once you're in flight, that's a bad time.
So making predictions is a good idea too, right?
Yes. Yeah. So I think ultimately to solve the sort of information security crisis, we're going to have to look at which tools we want in the right situation. So if you're building a rocket or a plane where you can't afford to find it on the fly, then you're going to want to use tools like this and approaches like this where you find it up front. There might be contexts where failure is okay, and then you can do lots of dynamic instrumentation, catch it then and fail gracefully before you allow some sort of correction or surrender of control. And I think one of the reasons DARPA and the military in general seems more interested in these approaches is that I think they're in situations where they don't want to find failure late; they want to find it early. But I think for like a lot of web apps, graceful failure is probably fine, rather than allowing an injection attack. So ultimately we need to approximate a set of visible states in some way. So now we come up with some secondary transition relation that will take us through some abstract state space, which models or abstracts over the actual execution of the program. And to do this, we need some sort of abstraction relation that connects together the original execution of the program and this abstraction. That basically says that we're going to stay in some kind of lockstep as we evaluate both of these machines so that anything that could happen in the real execution of the program is going to be in some way covered by this abstract execution of the program as well. This is a little theorem you prove every time you do abstract and abstract machines. And once you prove that, that's what gives you the soundness property that says, okay, I know that anything that could happen in this program, I'm going to see it reflected in this abstraction. And what that means is if you can't find, say, a buffer overflow, or you can't find an integer overflow in the abstraction, then you know you can't find that integer overflow, or you can't find that buffer overflow in any real execution of the program as well. So I'll step now through the high-level steps for abstracting abstract machines for a relatively standard abstract machine model, the CESK machine. And step number one is to sort of diagnose the problem, which is to say, well, why is it that when you execute programs, they may not terminate? If we want to take termination, and crush it down into something that does, why could it possibly go on forever? So the real issue here becomes apparent when we start looking at the state space of these programs. So if you blow up an individual state, you can look inside of it and see where this unboundedness comes from that allows potentially an arbitrary number of states to be visited. So there's really three places in here where we have a problem. We've got a frame within an individual machine state. We have an instruction, a frame pointer, memory or the heap, and a stack. And three of these can be potentially unbounded. So we could have an unbounded number of frame pointers. We could have an unbounded heap because we're thinking in sort of an idealized machine term. We're not thinking about a machine with an actual finite amount of RAM. And a stack can grow without bound too. So all three of these present challenges for us when we want to do some kind of abstract execution of a program in this model. So the goal behind abstracting abstract machines is to cut this unboundedness out, to some way erase it so that when we execute these programs in some new state space, we're guaranteed to terminate. So that's why step two is abstract. And in the simplest case of abstracting abstract machines, and we'll talk about more complex cases in a little bit, abstract means finitize. We want to take the state space and crunch it down to a finite state space. And what this does is it gives us a finite amount of room to run, so that no matter how long this program runs, eventually it runs out of gas and it has to stop. It says, okay, well now I've given you your approximation. So to understand finitization, again, I'm going to step you through this entire process for a CESK machine. And again, this is a well-known abstract model of execution where you model your machine with four individual states. So as you're stepping from state to state, these are the four components of that state. You have a control component, which again is probably something like your instruction, or if you have a function language, this is your current expression or your context. You have an environment or a frame pointer, you have a store, and you have a continuation, which is otherwise known as the stack. So from the CESK machine, we can look at the structure of this abstract state space. And it looks something like this. So for control, it's a set of instructions. For your environment, it's going to be something that tells you, given a variable, what the address of that variable is. So we're going to use a slight indirection for looking at the values of variables. You can imagine going directly from variable to value. And there are ways of dealing with that if you want to take that approach as well. But it's sort of pre-factoring the semantics so that things work out a little bit better for this demo. And then we have a store, which, given the address of a variable, will give you its value. And then you have the continuation, which is a list of stack frames. So we have a list of stack frames to model the stack. And this is, this is a pretty, if you really sort of cut a program in half as it were running, this is more or less what you would see in any individual state. So there's several points in here where we're going to have to inflict some kind of finitizing approximation. So the set of addresses in this idealized setting, clearly that's unbounded. So we're going to have to in some way finitize the set of addresses. But there are other things that are unbounded too. I mean, obviously if we have a list of stack frames, this could grow without bound. You just keep pushing forever. And so we're going to have to finitize that in some way as well. And we have the set of values, which include things like integers, which obviously, in the idealized model, also unbounded. So we're going to have to inflict an approximation there too. That's what we're going to do now. We're going to step through the components of this machine and finitize them one by one, and end up with an abstract state space that we can then execute. So, starting with value, let's look at what value would be in, say, an object-oriented setting. A value would be an integer plus some object, or the set of values would be integers and objects in a very simple object-oriented language. So let's approximate the integers first. So we'll take our set of integers, which goes from negative to positive infinity, and just say, well, now instead of having integers, let's just have sets of signs. So that we're going to approximate any value in the basic value program with the set of signs that that integer could be. So if you have -4, that's just negative now. And if you don't know whether it's, say, negative or positive, then you have a set that's negative or positive. And so as you do arithmetic operations on these abstract integers, you'll slowly start to lose precision. And you might end up in a situation where you don't know what it is anymore. But sometimes you can gain precision too. And if you square, negative, 0, positive, then that becomes just 0 or positive at that point again. And that's our set of, in this very simple example, that's our way of finitizing the set of integers and coming up with a set of corresponding operations for regular arithmetic. And then for objects, well, an object is a class paired with an environment. Or an environment here, sometimes takes a variable name and maps it to an address. So if you want to look up a field within an object, what we're going to say you're doing is you're taking the name of the field and you're going to get its address back from this object. And so we're going to finitize environments in just a second. And so once those are finitized, then objects are also finitized as well. And the key thing to remember here is that, or one thing to point out here, I suppose, so there's a correspondence between functional languages and object-oriented languages, which really shows up more or less just here. So if we were doing a functional language instead of an object-oriented language, then this would pretty much be where the chain shows up. When we're modeling closures are basically objects. Instead of classes, you have the lambda term, and instead of the record which defines the environment, then you have, or which defines the values of the fields, you have an environment which defines the values of the free variables. So structurally, these things are very, very similar to one another. Now, it turns out that while you can use the same model here, there actually is one interesting degeneracy that shows up in object-oriented programs. And this actually means that the complexity, sort of fundamental complexity of the analysis for object-oriented programs is lower than for functional programs. But that there's also ways to go the other direction, where you can take the richer structure that comes from analyzing functional programs and project that back into object-oriented programs as well. And actually go the other way too. You can come up with a cruder approximation of functional programs by using the same insights which you get for sort of by accident in object-oriented programs. And we wrote a paper about this years ago, and that's another great field. Yeah. So if you're interested about the interconnection between analyzing object-oriented programs and functional programs, this is an interesting paper to start looking at. But once you have an approximation of integers, and once you have an approximation of closures, then you have an approximation for values. So backing all the way back out, we've got an approximation for values now. So let's continue moving through the state space, approximating things, until we get all the way back to the top level. So let's approximate addresses next. And the way we're going to approximate addresses is just to declare that there's a finite set of addresses, and there is some map that exists between them. So for any real address, you can get its abstract address through some magic function right here. I'm not going to talk a lot about this function today, but it turns out, and in fact, if you want to know more about this, you have another excellent resource. My former PhD student, now your postdoc, Tom Gilbert, sitting in the back right there, who thinks a lot about this function right here and the magic that it can do. So tweaking this function right here can do lots of interesting things for the speed, complexity, and precision of your analysis. Yeah, there's a lot more to say here, but I'm just going to gloss over all of that right now. So that there exists some function that will some way give you an abstract address for a concrete address. And if you're wondering what's, in the simplest case, what this might look like, just imagine the function that returns only one abstract address. So you can take the entire heap and crush it down to one address. If you really want to get that approximate. I mean, it's not going to give you great precision, but you can do it. So now we have finitized addresses, we have finitized values. The last thing we have to finitize is the stack frame. And one thing to point out is that once we moved to a world in which a single address in this abstract, in this analyzer world, can represent multiple character addresses, there is a possibility that when we look up an address, more than one value can come back. So if we have one address, so like again, suppose we have a universal address that represents all addresses. If we look that up, it's got to potentially return all the values that are live in that program. So we changed the range of the store to be a power set at this point, so that we can hold multiple values at any given location. And now we just have to abstract stack frames. So to abstract stack frames, we're going to just first play with the definition a little bit. We're going to say that, well, a list of stack frames is really the same as this recursive data structure right here. And we can use a technique for cutting out recursion by threading things to the store to ultimately get back to a point where we sort of move the unboundedness of the stack into the unboundedness of addresses. And since addresses have just been bounded, we take away the unboundedness of the stack at the same time. So to do this, what we do is we say, okay, when we have a continuation within a continuation, let's actually have it just be an address. And what we're going to do then is put continuations in the store, so we can then look up the next one. So moving back to this high-level state space, we're going to say that in addition to getting a value back from the store, you can also get a continuation now. So when you are traversing down a stack frame, if you want to get to the stack frame beneath you, you actually have to take the address that's in the current stack frame and look up the continuation right beneath you at this point. So we're threading that unboundedness through the store, and then, since we've already finitized the store, we get a finite number of stack frames as well. So this general process, what I've done is I've run a specific instance of this general process called abstracting abstract machines on this somewhat generic state space that you can use to interpret both, say, functional programs and object-oriented programs. And there's a corresponding set of transformations that goes on when you do this inside of semantics. And once you do this, you get an abstract machine. So to just show you what this looks like in the semantics world, this is a concrete semantics right here for a Java-like language. And when you push it through this process, you get a somewhat similar looking set of rules out the other side. But these now obey the constraints you've imposed through this approximation process. So that's sort of a lightning fast tour of abstracting the abstract machines. If you want it in more detail with a real live coded example, there's a video I have online and a blog post that goes with this, which works through this entire process, again, in a live coded fashion for a very simple imperative language. So it's like really a register machine kind of language. And I read it the interpreter, I read it, and I slowly transformed that into the analyzer in real time. So it's about an hour and a half long, but if you really want to know more details, I definitely recommend watching that video. So what I've just described is a pretty general process for taking almost any kind of language and getting an approximated for it. And the question is, can you use this in practice now to reason in a meaningful way about what a program will do so that you can solve real engineering problems? And the answer is yes, you can do this. And to give you an example of exactly this, I'm going to step you through sort of the punchline phase of a program that David and I also did called APAC. So this was a fun effort between David and I where we teamed up and we're trying to reason about cybersecurity problems in Java. And I'm just going to say that this entire program is premised on what might be one of the worst ideas I've ever heard. And the idea, of course, came from the military. And they said, wouldn't it be great if every soldier had something like a smartphone? And then you can have like the App Store, and they're on the battlefield, and they'll download the Drone Strike app, and they'll drone strike people. This is obviously to us, I think, a pretty bad idea. But to them, I thought, oh, this is the future of warfare. Let's go ahead and do it. So as soon as, they really did have this vision of having like a military app store that third parties will submit to, and somehow magically everything is going to be secure. So what could possibly happen with this? Well, one obvious example is, well, let's suppose that somebody submits a malicious mapping application, which is silently transmitting your location to some third-party adversary. I mean, this is one of many, many things that could happen under a scenario like this. And so the program APAC was conceived as a way of building some assurance that contractors submitting programs to this app store wouldn't be able to do this sort of thing. The idea here is, in APAC we were building these app auditors, and this is going to be the barrier between the outside world and the app store. So somebody submitted an application to the app store, it would go through this auditing process, and if it was good and benign, we would scan it and realize that it was okay, we'd let it through. And if it was a bad app that was trying to do something malicious, then we would scan it and find out that it was bad, and we would not let it into the app store. At least that's the theory behind program APAC. And of course, halting problem. So how are we going to do this in practice? What does this mean? How can we actually take Java programs and in advance look for signs of maliciousness? Well, I will tell you in the abstract how we did all this in the end, but let me just show you how we did. So about 6 months of the program, when this program was kicking off, and we turned in our very first analyzer, we had to do an engagement, and we got a 0%. Like, we actually got nothing right. It was somewhat of a disaster. I remember sitting in the meeting and explaining to the PM at DARPA that sometimes there's a difference between the vision you submit in your proposal and the deliverables you get at the end of the day. And if you were to go back and read our contract very carefully, he would notice this difference as well. But actually, over time, we really took off and it did quite well. So by the end of the program, for these week-long engagements that we were doing, we actually were scoring at 100% accuracy, meaning we were correctly predicting, yes, this is malicious, no, it was not, and when it was, why it was, and what the reason they actually intended it to be. So this was exciting to see that it was possible. But what made it possible was a heck of a lot of research. I mean, this was an engine to fuel a lot of innovation in the field of static analysis, and I'll just give you a survey of what some of that stuff looked like right now. So I think one of the biggest innovations to come out of this program was a shift from finite state analysis. Yeah.
So how exactly do you know that you caught everything bad? I mean, you don't really know what you didn't catch.
That's a great question. So the way this program was structured was they released apps to us, and we had to serve as the app auditors, and they deliberately implanted malware in some of them and not in others. And it wasn't enough to say yes or no, because ultimately all of them were wrong, and many of them were malicious. But if you didn't say exactly the maliciousness that they had implanted in the program, then you got it wrong. So you had to find exactly what they planted in the program. So this was their way of getting it. So it's an approximation of ground truth. So there could have been maliciousness in these programs that they didn't plant in there either, that we didn't find. So there was the possibility that we would miss that. But because they had put certain things in there, that when we would find it, with that accuracy rate, they were pretty certain that we had a reliable tool.
And in each engagement, you got a new set of software that you've never seen before?
Yes, in every engagement, it was a new set of programs. Although they actually sometimes would modify one or two apps from a previous engagement. Maybe one that wasn't malicious previously that now was, or one that wasn't. I mean, they would do evil stuff like that too. But mostly new programs every time. Yeah. So one major innovation that helped us overcome a lot of obstacles, particularly in terms of precision, was a shift from finite state analysis to push-down analysis. So earlier I said that when you abstract, you finitize everything. Well, this is a pretty severe approximation of program behavior. It turns out it's a little more severe than necessary, because there's levels between DFAs and Turing machines that are still computable for many properties of interest. One of those levels is pushdown. So you can allow the stack to be unbounded in these machines and still compute lots of interesting properties about these models. So the way this works is, instead of having in every single machine state the four components that include the stack, you pull the stack out, and on the edges, you annotate the edges with a stack change. You pushed a frame, popped a frame, or didn't change anything from one state to the next. So at a high level, that's what you're doing. There is a fair amount of changes to the implementation at the end of the day. But this shift gives you a pretty dramatic improvement in precision for reasoning about the programs. And weirdly enough, sometimes also improves the performance. But that's not entirely uncommon to have happen in static analysis, where improvements in precision end up cutting away large swaths of state space which are strictly impossible or strictly over approximating. So sometimes improvements in performance, improvements in precision become improvements in performance as well. And we've had a long run of interesting papers playing around with this idea and adapting it in different ways. We've come up with a number of ways to take abstract and abstract machines and optimize the performance of the analyzers that come out. We've figured out not only how to analyze parallel programs, but also how to analyze programs in parallel, again, all within this framework. We figured out how to do information flow analysis by enriching the states to include what we call a taint store, and we've applied this to things directly like malware detection. So this is a very fruitful research program overall, I would have to say. And we're now involved in a successor to this called STACK, where we're looking for space-time vulnerabilities in programs, as far as space-time and complexity vulnerabilities in programs. And our general approach to this is to build a similar kind of approximation and look for individual regions within the program that we classify as what we're calling algorithmic units. And then what we want to do is take these individual algorithmic units and describe their complexity in terms of recurrence equations. And then what we want to do is take the recurrence equations and pass them through solvers so that they will tell us about the high level complexity of an individual region of code. And we can, once we have a tool like this, then we can use it to start things like complexity attacks, where somebody would send an input to a program that, even though the algorithm is correct, it takes an intractable amount of time to compute the answer. So this can happen with things like, for instance, regular expression matches. So you can, sometimes for some implementations of regexes, you can find inputs which cause a tremendous amount of time to actually compute whether or not there's a match. And then space attacks are similar. So instead of using up a lot of time, you can end up using a lot of space. And then of course there are side channels as well. And so all of these are within scope for this research program. So that's a very, very high level summary of how we fix software. So how do we fix people? Well, let's talk about what goes wrong with people and how to fix them. And to fix them in a nutshell, we need something called precision medicine. And this is what I actually spend most of my time working on at the White House and most of my time working on at the Harvard Med School as well. I do very different things at different scales at both those places, because at the White House I'm very focused on the Precision Medicine Initiative, which is a monumental effort to enable the sort of basic data science to allow precision medicine in the clinic to happen. And then at the med school at Harvard, I work on the clinical side, where I take individual patients and try to find the perfect drug for them. So the precision medicine as defined by the president when he kicked off this initiative almost 2 years ago now, is that it's data-driven medicine, where you're taking lots of data from individual patients, usually genomic data, this is the new data set we have access to, and trying to map the right drug to the right patient. This is the goal. And now, with that in mind, what I will say is that I think precision medicine is exactly the way we want to go about curing cancer. But that curing cancer is very hard. In fact, curing cancer is probably the hard case of precision medicine. And that's because cancer is not a disease, despite what you may have heard. Cancer is, in fact, many diseases. There's no one disease that is cancer. In fact, it's many rare diseases. And it's arguable that any two people have ever had the same cancer, because everybody's got individualized genomes. And then, even within a single patient, between two tumors, even within a tumor, you may not have the same cancer because cancer mutates all the time. So curing cancer, if you take sort of a reductionist view, comes down to curing rare diseases. So let's talk about how to cure rare genetic diseases. So to do this, I first have to give you some very basic intro to biology meant for programmers. So DNA is a string, and it's got 4 letters, A, T, C, and G. And these 4 letters are encoded chemically as nucleotides, which make up this double helix, which is DNA. And the way a really important portion of our genome works, which is called the exome, the portion that codes for protein works, is you start off with DNA. This gets transcribed into RNA, and then RNA becomes translated through ribosomes into proteins. And proteins are sort of like the fundamental machines within the cells. They can act as structural components, but they can also act as components that enable chemical reactions to happen. So much of life really involves involves creating proteins. And the way proteins are built is you take RNA, you divide it into segments of 3 base pairs at a time, or 3 nucleotides at a time, and then you translate each of those into a particular amino acid. So these amino acids get strung together as a polypeptide, and then depending on the particular side chains hanging off of these amino acids, they will start to fold. This string will start to fold into a 3-dimensional structure. So And that folding is guided by things like the pH of the surroundings, and also the particular polarities or electropositivities of the side chains involved. And then you get a three-dimensional shape from that. And that three-dimensional shape will either be structural or again, it will compute some reaction. It's a little more complicated than this because proteins also get modified. Things will get stuck onto them, things will get cleaved off. But for the most part, this is really how the compute of it is inside of each of your cells is really working. And in fact, one important observation to make is that many proteins are enzymes. Enzymes are actually things that enable reactions to occur. So they will take some precursors and turn them into outputs. And this can go in a number of ways. So you can take several things and make them into one thing, or you can take one thing and then make them into several things, or you can do both at the same time. You can take several things and make them into several other things. And the interesting thing about this is you can describe these enzymatic reactions almost kind of like functions. It's got inputs and it's got outputs. And what this means is the genome has not only syntax, but it has a semantics as well. It has it sort of at multiple levels. And DNA is really kind of an instruction set. So just to give you a sense of how this works, here's the instruction set for a very, very simple protein. And what we're going to do is actually convert this into a more readable program that's describing what exactly it's doing. So ATG is the instruction sequence that encodes start construction of a protein and insert a methionine. And the very next sequence, GCC, does what? So what does GCC do in the context of DNA?
Does it compile C?
It compiles your C program. It is a very complex codon. Surprising to find it in our DNA. No. So GCC in terms of DNA actually just means insert an allele. And TGA means, since it's the last thing, guess what it means? Stop. It means you're done. So putting all that together, what you have is this program right here, which will build a 2 amino acid protein. And then now we can understand what mutations are doing when stuff goes bad. So we can take this program, we can mutate it so that we have a C there instead of an A there instead of a C, and then we get a different program. We had this program, but after this mutation, now we have this program. So it inserts an aspartic acid instead of an allele. And the thing is, that may not actually do anything. That may be a perfectly benign change. It may not change the structure or the function of the resulting protein much or at all. And again, in many cases, this is exactly what happens. But some of these mutations will actually destroy the function of the protein. And some will increase the function, which could be good or bad, and some will change it entirely. So, this is what happens when your DNA starts to mutate. And rare disease, by and large, are caused by one mutation. Usually it's just one mutation in just the wrong place that ends up giving you an entire disease. So to give you an example of this, I'm going to use my favorite model organism, the stick figure. And I like the stick figure as a model organism because it has only 5 or 6 genes, basically one for each body part. And so if we have a mutation that knocks down the function of the C gene, then it might do something to the resulting organism. And in this case, it shrinks its head. So clearly C is associated with head size. And what this means is if you're looking for a cure for the small head disease for stick figures, what you're looking for is a drug that will do the opposite thing to C. You want to drive the activity of C up at this point. So that's the drug in this case. Now, if you find it, then hopefully, and you administer it, hopefully the head gets bigger. That's the idea. But cancer is inherently multigenic. So when you're dealing with cancer, it's rarely just one mutation that's involved. And it gets worse than that. So in cancer, you can have, for stick figure cancer, you might have these 3 different genes, some of which are now overactive, some of which have become underactive, and all of these are contributing to this proliferation of growth of some tumor type. And so you want to come up with a cocktail of medications potentially that will ultimately be able to compensate for all 3 of these genes being out of alignment. But what often happens is by the time you find that cocktail, yet another mutation has occurred, which is enabled to circumvent whatever original intervention you came up with. So, and this is because tumors evolve. And in fact, I would argue that the way we treat cancer currently actually encourages that evolution. Because the way it works now is that if you get a colony of cells within some tumor, remember these are mutating all the time, or these frequently mutate. And so what you really have is several different cancers even within the same tumor. And suppose you apply some drug that's designed to target some of these tumors. And it wipes out everything but the blue, because blue happened to have some mutation that compensated for that drug, and the blue got to survive. Well, that blue is still a cancer cell. It's still going to keep proliferating, but when it proliferates, and continues to mutate, it's going to remember how it evaded that first drug. So when this colony comes back and expands, it knows how to defeat the drug you gave it the first time. Not because tumors are smart, because they're just using evolution. This is what they do. So the same drug stops working over time in cancer. In fact, in the way that we attack cancer, where we do one drug at a time, we're basically building super cancer slowly over time. Because we say, okay, first become resistant to this drug, now become resistant to this drug, now become resistant to this drug. That's the way we treat cancer right now. So curing cancer is like curing many monogenic diseases on the fly, all at once. So this, as it turns out, is hard to do. Because even curing one monogenic disease at present is kind of hard. And I'm actually lucky that I just picked up an NIH grant to do a pilot project on exactly this. So I'm taking a small set of monogenic diseases, probably 2 or 3, and we're going to try to see just how fast, under ideal conditions, meaning I get to pick which diseases I want to cure, we can actually find a treatment for them. We estimate it could be anywhere between 6 and 12 months. So there's turns out, over the past few years, I've been mapping out a process where you take a patient and ultimately end up with a drug. And I'm not going to go through the entire process in detail now. This is an entire course, not just one lecture to do this. But really it starts off with sequencing and moves through this process of interpreting the genome and figuring out what's ultimately been disease-causing. And it branches on things like, well, what exactly how did the protein change? Was it a gain of function, a loss of function, a change in function? What's going on to really drive the disease? And depending on how you branch in here, it will either tell you need to go run this experiment and then do this thing based on the output, or this might be a reasonable drug for you. And ultimately you end up in something like clinical trials, which is unfortunate because that's an awfully difficult step. The question is, will it work? Can we actually rapidly discover treatments to new diseases? And to tell you that we can, I'm going to tell you a personal story, which is how I got involved in all of this in the first place. So up here is my son Bertrand. He's 8 years old, and when he was born 8 years ago, we actually didn't know what was going on because he had unexplainable movement disorder, developmental delay, seizures, and for some reason he also couldn't cry tears. He's got some other stuff, but those 4 symptoms are sort of the main ones that we deal with on a day-to-day basis for him. I just started as a professor of computer science at Utah, and ended up on this odyssey, trying to figure out what was wrong with him, and then ultimately how to help him out. And so for 4 years, we had no idea what he had. We tried literally everything. We actually ran out of diseases to even check for. And eventually, I realized we had to do we suspected it was genetic, so we have to do sequencing. We have to look into his DNA and figure out what mutations are driving this disease. And at the time, this cost like $500,000 to do. But around that time, a new kind of sequencing came out called exome sequencing, which is orders of magnitude cheaper. And we were able to get into a research study at Duke University that was doing exome sequencing to look at just the protein coding portions of the genome. And what they found was that my son actually appeared to be the very first case ever discovered of a disease caused by mutations in a gene called NGLY1. So they found these mutations in this gene that appeared to wipe out the function of the gene. And then they said, he appears to be the first human being ever affected by a disease caused by this gene. He's the only patient we know of, and in many ways he's an N of 1. So everything, we can't give you a prognosis. We can't even be really certain that this is the cause. Because again, no one's ever linked this gene NGLY1 to human disease ever before. And by the way, if this is the cause, it's also one of the rarest diseases in the world. There's probably about 500 people total living with this disease somewhere. So it's sort of a 1 in millions type disease. So how do you know? I mean, how did they know? How do you know when you find new mutations you've never seen before and then claim that this is the cause of disease? Because we all have tons of mutations. There was lots of mutations in this genome. They could have picked. How did they feel confident about this one? You might imagine some really principled approach to do this. We do molecular dynamics. We take mutations, you model their effect on resulting protein structure, and then you check to see whether or not this actually makes a difference for the enzymatic activity of the protein in this case. Unfortunately, that view of the world where you simulate behavior of a protein is just completely unscalable. You just cannot do that. Past a certain number of atoms, it's just intractable. So that's not what we do in practice. What we have to do instead is come up with a workaround. And in fact, this is what the Precision Medicine Initiative is all about, is coming up with this workaround for understanding the human genome. So we're building a cohort of 1 million Americans and asking all of them to volunteer their genomes and their health data, and even things like Fitbit data, so that we can figure out gene disease environment correlations. This is the whole idea behind this project. So 1 million Americans are going to donate their genomes, and essentially allow us to build what I would call a genetic telescope, so that we can peer into any region of the genome and say, okay, if you have mutations here, what is this doing to the health of the humans in the study? You know, is it making them more predisposed to heart disease or less predisposed to heart disease? Or does it give them apparently a rare disease? So that's really what this project is about. That's what I spent a large fraction of my time working on at the White House. And if we do this, if we get this right, then we will be able to start teasing apart the regions of the genome and figuring out when you have mutations here, or when you have this mutation in particular, this is what it means for you in terms of your health. And I'm also in charge of, or really not in charge of, I consult very heavily for another program that's very similar called the Million Veterans Program. We're doing the same thing with 1 million veterans. And the advantage of this one is it's not new. It's been around for about 5 years. We already have 500,000 veterans enrolled. The only issue there was that we lacked the computational capacity to actually start interpreting all the data that was coming back. So I've assisted in an arrangement between the Department of Veterans Affairs and the Department of Energy to get VA data running and crunched on DOE machines. Because DOE has no shortage of hardware for doing this sort of stuff. But it turns out legally it's quite difficult to move data outside of the VA. You basically have to turn DOE into a part of the VA to do this, and that's exactly what we did. And then put data on a truck and drove it because that was the fastest way to get it there. And there's lots of studies that we're just starting off now with the VA. So we're looking at genetic factors for PTSD, for schizophrenia and bipolar disorder, for Gulf War illness, for cardiovascular disease, for chronic kidney disease, for metabolic disorders like diabetes, and for multi-substance abuse. So we're using that data to figure out the genetic factors that influence all of those diseases and potentially provide drug targets that we could use to then treat these disorders as well. We're also looking at macular degeneration. All right, so that's all good. Well, what about my son's mutation? You know, what can we do for him? So to help him figure out whether or not this was really what was wrong with him, I wrote a blog post. Because again, they said we think this is it, but until we find a second patient, we really don't know if this is exactly what it is. And in this blog post, I really decided to do two things. It needed to go viral, and it needed to rank highly in Google search results for any patient out there that might be searching for the same thing. So this is the blog post I wrote. The picture of Liam Neeson is to make it go viral, because the internet is sadly predictable like that. I think a cat picture probably would have worked pretty well too. There's 5,000 words below that to help with search engine optimization. So it actually did go viral, seen by millions of people very shortly. It did end up ranking very highly in Google search results. And sure enough, within literally 2 weeks, we started finding more patients for this disease, which again, 2 weeks prior, like nobody even knew existed. And today we've had patients popping up literally all over the world. So 4 years later, we actually have 57 patients total for this disease. What this has done is it's really washed away this dark night of uncertainty and replaced it with the sunlight of science and community for us. And to go over 8 years from having no idea what this disease was, to finding it was the first case ever of this big disease, to finding that we actually had a community, that was a pretty remarkable process. Ended up getting written about in the New Yorker. The reason I ended up in the White House is the president read about it and asked me to come meet. And it was through this article. And then I've been very focused on finding a treatment. And it turns out I think we've been sort of unbelievably successful here as well. And this becomes sort of the template I've been using for curing other diseases. It turns out you can model the sort of the broken enzymatics of this disease in a formal system. It turns out you don't need a formal system to actually do the reasoning, but you can. There's a language out there called Kappa that will do it for you. So Kappa is a systems biology language. And you can use this or pencil and paper to make predictions about what's happening inside my son's cells. And it turns out that if you take out this enzyme NGLY1, then what it does is it's responsible for deglycosylating misfolded glycoproteins after they're retrotranslocated from the endoplasmic reticulum into the cytoplasm. Again, one of those sentences I never thought I would have to say as a parent. You can model what this missing enzyme will do to a cell. And you can say, well, it looks like it's going to lead to an accumulation of misfolded glycoproteins. It also looks like these misfolded glycoproteins are going to end up with sponging off a particular metabolite and basically locking it away so that you become deficient in this substance. And that substance in this diagram here is represented by this little blue square. So what I did is I Googled for those little blue squares called N-acetylglucosamine, and I realized that you could buy it on Amazon. So I bought it on Amazon. I took a bottle of it myself, and it didn't kill me, which is great. So that constituted safety testing. Because in my household, I really am the FDA. They really do insist on this disclaimer. And then, about 3 days after he took it, something remarkable happened. He actually started crying tears for the first time in his life. And this is something that's been replicated with other patients with type 1, where they also start crying tears when they take this substance. So, for us, it was sort of one small tear, and actually he's had many tears since. But really, I think it represented an ocean of science for type 1 as a whole. So this was definitely, I was shocked as a parent that this actually worked in his capacity whatsoever. And we actually saw, over a couple months, a complete elimination of his nighttime seizures as well. So this was not small. This took away about half the symptoms he was suffering from pretty effectively. Now, the interesting thing is that we knew it worked in humans. And the question we all wanted to know after that was, does it work in flies? So I partnered with a human geneticist. We gave these poor flies the same disease by knocking out the gene. And if you take out this gene in flies, or the ortholog thereof, they have about a 70% survival rate. However, if you raise them on this compound from birth, the survival rate goes close to 100% in many cases. So this is a shocking turnaround in the progression of the disease. And the reason this is ultimately important is now we can publish it. We're academics, and we want to publish it, but you can't publish anecdotal data from humans, but you can publish data from flies. So the question is, will it work again? And it turns out I'm also a co-founder of this company, Paranomics, which does exactly this as a service. If you come to us with a rare genetic disease, we'll run through a process like this for you. And we're really focused on genetic epilepsy primarily at the moment, because we have some techniques there. But we can screen thousands of available compounds and see if any of them will make a difference for your cells. And it turns out we actually, looks like we have a first success story, even though we're not even a year into our operation. Looks like we're going to find a treatment for pretty devastating rare genetic epilepsy right off the bat. And ultimately, precision medicine is about more than computation. I think there's a lot of regulatory barriers at the end of the day as well. So once you get a diagnosis and find a therapy, you actually have to get this approved. This is what I spend probably another third of my life doing now, which is advocating for the changes that have to happen to make precision medicine possible in reality. So I've spoken in the House, I've spoken in the Senate, I've met with leadership in both the House and the Senate. I've worked nowadays with leadership at both FDA and NIH, and even within the highest levels of administration to make sure that the kinds of policies and regulations and laws that need to be in place to make this kind of medicine possible in the first place are going to be there as the science makes it available. And in fact, I would say the science is ahead of us. The science has already made it possible, and so in some ways we're really playing catch up with the regulation. And I would encourage everybody, since ultimately we are all at the end of the day patients, and about half of us will get cancer, since you're also in DC or close enough, you should be on the Hill. You should be lobbying for, or not lobbying, but advocating for reform to agencies like the FDA to make sure that we can make precision medicine possible in the clinic when the time comes. So, to summarize, I would say that the war on error is a long one, but one that has hope, and that through approximations for things like the halting problem, and this process of mapping patients into our medications, we can ultimately win someday. Thank you. Yep.
So let's assume that we're able to run this process on, let's say people who hadn't, like fetuses who hadn't delivered their children yet, and you were able to match them up with some compound. Do you think that if they, if you were able to get regulatory approval to be able to do this, do you think that that would improve sort of the prognosis even better past after birth?
Yes, absolutely. So first of all, this is possible. This sort of thing does happen now. You can sequence an unborn child's genome. In fact, you can sequence an unborn child's genome from free-floating DNA in the mother's blood. So you can take a blood drop from the mom and reconstruct the fetal genome. This can actually be done. And yes, you can diagnose genetic disease extraordinarily early. And in almost every case, particularly when there's a developmental component, the earlier you intervene with treatment, the better the prognosis. So that is already a reality. The question of whether or not the FDA will allow it comes down to whether or not the compound is approved. And if the compound is not yet approved, well then you're in trouble. Because regulatory approval is not easy at all.
Great. What's the regulatory approval of the compound that you discovered?
You buy it on Amazon.
Huh?
Just buy it on Amazon.
So if someone had an unborn baby diagnosed with type 1, would they be able to treat their child with that?
Yeah, they could. They can also buy it online. Now obviously the FDA hasn't ruled on the safety or efficacy of this compound,
Right.
but we believe it to be very both safe and efficacious.
Finitization seems to be a main trick, for, at least for the first part of the talk. Do you have any ways to reason about the quality of finitization?
The quality of what?
Finitization.
Oh, the quality of
finite. And the
Yeah.
second thing is what are the limits of your mind of your approach?
Sure. So I think the yardstick we use for the quality of the approximation is usually some end application. So you can imagine some sort of gold standard where for a given kind of approximation, you could run a suite of programs that you know are terminating. You could abstract them into sort of the ideal abstraction of themselves and compare that directly to the approximation you computed. That gives you some sort of abstract version of how approximated it would become. But I think the way we like to measure the quality of the approximation is in the end result. Like how much better are we at finding malware? How much better are we at finding vulnerabilities? How much better are we at optimizing programs? I think those are the yardsticks we like to use. So I think you could take two directions of this. You can come up with some abstract measures, or you can measure it with the end result. Under both metrics, I think we're strictly improving over time quite well. We've gotten pretty good at building these tools that will help you find malware. We've gotten pretty good at building tools that will help you optimize your programs.
How do you know that abstraction itself is not changing the behavior of the program?
Yes. So how do we know that the abstraction is somehow not missing behavior in the program in some way or modifying it? Yeah. So we have to prove a theorem every time, a soundness theorem, that shows that there is a relationship between the original interpreter and the approximator. And what we show is that if you start off with a concrete state, an abstract state, and you take a transition in the concrete world, there must be some corresponding transition in the abstract world that keeps these things in sync. So that no matter how far you go out of the concrete execution, there's always a way to find a corresponding abstract execution as well. So this abstraction relation gets maintained. Yeah, and that's how we know that all behaviors are covered in the approximation. It's also how we know that some impossible behaviors are going to be covered in the abstraction. We're going to include stuff that certainly can't happen in the process of becoming finitized.
What do you see as sort of the biggest forces standing in the way of progress on regulation when it comes to precision medicine? Like what's preventing that?
In my view, and this is me speaking personally, not as the president, the FDA has a very strange incentive structure. They get almost no reward when they approve a drug that works. And they get crushed when they approve a drug that causes any kind of harm or may not work. So this creates an incentive system where by default they want to reject it. It's kind of like peer review. By default you reject. And there's very little incentive to actually let something through unless it's just so obvious that it's safe and efficacious. That's the problem that we're really up against. And we have a one-size-fits-all model for how we do approval. We say whether this is for heart disease or diabetes or whether it's for a disease with 30 patients in the world, we're going to use the same regulatory approval mechanism. And whether the disease is severe and life-limiting as end-stage cancer or it's the common cold, we're going to apply the same regulatory approval structure yet again. So we don't account for the severity of diseases, and we don't account for the scale of the populations to which they'll be applied. And if we don't start allowing some tweaking here, then we're missing lots of opportunities to improve medications. So my personal view is that we need to start decoupling, at least in rare disease or life-limiting diseases, safety and efficacy approval. So once something is safe, if you intend it to be for a rare disease, it should be on the market. That's my view. And we'll worry about proving efficacy later on, because for many diseases they're fatal, and even when they're not fatal, they're awful. And the same goes for cancer. I think we probably want to err on the side of giving patients more choice over what they'd like to do, and worry about cleaning up the data science later on. I just think this makes way more sense because right now we're in a situation where frequently it's the case where we know there's a medication in trials that will likely work for some patients, but we can't and don't give it to them. This is happening to my son right now. There's a compound that we know works very well in cells, but it's going through regulatory approval for a completely different disease. And we can't join the trial for that disease because we don't have that disease. And so we're waiting for this compound. We already know it's safe. It's already been through safety testing. We're waiting for it to get approved for a completely different disease so we can take it for this disease. This doesn't make any sense at all. But that's the current system.
As a follow-up, is there a medical system outside of the US that does this better?
None that I know of. I mean, some are a little less. Europe seems to be a little more generous in approvals, but they all seem to face roughly the same incentive structure, which pushes them away from approving as the default.
Is that time?
Maybe just one more question.
So the success stories you talked about apply to Mendelian disease, you have specific mutation in exon.
Yeah.
But everything that we talk about complex diseases, most of the stuff is happening in the non-coding region. So
Sure.
what's your general approach to deal with those situations?
Yeah, so I think, so the question is, what I just talked about was a case where we're looking at disease caused by changes in the protein coding regions, which is about 2% of the genome. It drives virtually all genetic disease, but when you get into common disease like heart disease, where what you really do is you have multiple genes, multiple regions of the genome which influence predisposition. A lot of these end up in regions of the genome that don't code for protein, where you get these RNAs that float around and actually have regulatory activity in other parts of the cell, even sometimes other parts of the organ or organism. So we can apply, there's an algorithm branch there as well, I just haven't discussed it. So there's in fact a really interesting research program going on at NIH right now where they're looking at RNA itself as both a diagnostic and as a treatment. And so there's ways of encapsulating RNA in these things called liposomes so that you can effectively drugify it. And RNA is cool in the sense that if there's an RNA that you don't like, you can form its anti-RNA or an antisense RNA to that and you can wipe it out because it'll actually bind up and kill it. So there's lots of interesting possibilities going forward for using RNA to manipulate human health. I think we're sort of probably 10 years out from somewhat widespread adoption of these techniques. It's moving incredibly fast. You can also use this sort of like on-the-fly, temporary genetic programming, where you could temporarily give yourself a gene, or temporarily upregulate some process, and then once the drug dissipates, it goes away.
All right, let's take that.